Hello. Today I just wanted to make a little video on 2.6, kind of 2.7-ish. But today we're going to focus on what would be in 2.6 in your text, which is graphs of rational functions and asymptotes. So a lot of this will be review, and we're going to spruce it up a little bit with some new things for pre-calc. Remember, a rational function is the ratio of two polynomials. You have one polynomial in the numerator, one in the denominator. And one of the biggest things about the domain of a rational function is that it includes all real numbers, but rational functions have some restrictions. We want to exclude the x values that make our denominator 0. Okay, so let's just look at this, one of the simplest rational functions we can have. F of x equals 1 over x. Let's look at what our domain is. Well, we can know our denominator cannot be x. And so maybe in the past, what you guys did is like all real numbers or except that x cannot equal 0. But what we're going to do is we're going to write that in interval notation. And what that means is that we want to have all the numbers from negative infinity to infinity, but not 0. So the way that we write that is we're going to say negative infinity to 0 in union with 0 to infinity. That includes all real numbers except for 0, okay? This is the way that I'd like us to write our domain, is in that interval notation, okay? Now, as far as the range goes, it turns out that the range also is going to be limited. And the range ends up being that if we look, the only way that our output could be 0 is if our numerator is 0. You guys, there's no way that this is ever going to be 0. So for this particular function, what we're going to do is, again, it's all real numbers such that x cannot equal 0. But again, we're not going to write it this way. We're going to write it in interval notation. Again, we're going to say negative infinity to 0 in union with 0 to infinity. Okay. And so when we graph that, because of these restrictions, we have these different asymptotes. Okay. And so to find our asymptotes, the vertical asymptote here is going to be this line that represents something that our domain cannot be, all right? X is never going to cross that, so X can never be that. And notice that our vertical asymptote is at X equals 0. That corresponds to the domain, okay? Similarly, we have this horizontal asymptote. The horizontal asymptote, and we'll talk more about that kind of as we progress. Technically speaking, you can cross a horizontal asymptote, but in this case, we don't. Again, we'll get into that in a little bit. But the horizontal asymptote helps us know what's happening on the ends as x goes to positive and negative infinity. And in this question, our horizontal asymptote is that y equals 0. Okay? So those are some things that you may have done last year in Algebra 2. This year, we're also going to talk about vertical and end behavior statements here, okay, with the rational functions. So the vertical asymptote is going to lend itself to the vertical behavior. What that means is that on either side of the asymptote, what's happening, okay? So notice this says x approaches 0, and there's a little negative sign that's here, okay? This little negative sign here is really meaning on the left. Okay, so if we look to the left of the asymptote, then what is the function doing? Well, I see that to the left of the asymptote, the function's going down. So we're going to say that f of x approaches negative infinity. And now we want to look at the behavior to the right of the asymptote. That's what this is. This 0 plus means I'm going to look on the right of the asymptote, which is at 0, x equals 0. So if I look to the right of the asymptote, I see that my graph is going upward towards positive infinity. So these vertical behavior statements are things that, again, are new for pre-calc. We'll talk about what happens to the left and to the right of each vertical asymptote. We'll also talk about what happens as far as the end behavior. And we know that end behavior is what happens as x approaches negative infinity, where we're looking all the way to the left of the graph, and as x approaches positive infinity, as we look to the right. Well, we can see here that as x approaches negative infinity, that our graph is getting closer and closer to the asymptote at 0. So we're going to say that f of x approaches 0. And if we look at as it goes to positive infinity, it also approaches 0. This might be something that you've done last year, but we're going to, again, take it up one more notch. Not only are we going to say that it approaches 0, we're going to tell on what side of 0 it is. So if we look as x approaches negative infinity, then we approach 0, but below it. So because it's below that, we're going to put a 0 negative. And again, what this represents is it means basically like from below. Okay, so from below 0, we're getting to 0. Okay. And then as x approaches positive infinity, f of x is approaching 0 also, but notice that it's from above. And we're going to put a positive sign as a superscript to denote that. Okay. So those are some first new things that we'll look at, the vertical and very specific end behavior of our rational functions. Okay. Well, this is for a very simple rational function. Let's look at asymptotes of rational functions in general. Okay. One thing that is super important that we need to look at is that we look to see if the numerator and denominator have no common factors. That means we need to factor and see if there's anything in common in our numerator and denominator. Okay? If they do, there will be points of discontinuity, and those are going to appear as wholes. Okay? Again, this is something that's new this year for pre-calc. The moral of the story is there's going to be what's called a whole if we have common factors. And we'll practice that together. Don't you worry. Okay? So, what we know from last year is that our function has vertical asymptotes at the zeros of our denominator. And so to find our vertical asymptote, what we're going to do is we set the denominator equal to 0. Okay? And ignoring any common factors, any leftover factors we have, mean that we'll have a vertical asymptote. Okay? In addition to vertical asymptotes, again, f has at most one horizontal asymptote. And for the horizontal asymptotes, what we do is we compare degrees. Okay? So again, for the horizontal asymptote, we're going to compare degrees. Okay? So let's say that the degree of the numerator is less than the degree of the denominator. Remember, the degrees are the little exponents. Then that means the horizontal asymptote is y equals 0. If the degrees are the same, then what you do is you divide your leading coefficients. Okay? Now, last year, if the degree of the numerator was greater than the degree of the denominator, you just said there's no horizontal asymptote. But we're going to spruce it up some more. This year, we're going to say there's a slanted asymptote. We'll get to that in the next lesson. Okay? But hopefully, this idea is review for you, how to find the vertical asymptote and horizontal asymptotes. And then the new thing we'll look at today is finding a whole. Okay? So our first example asks us to find the domain of the function, identify any horizontal and vertical asymptotes, and identify any wholes if applicable. So first we want to factor. We can't do that. It's completely factored. We're good. All right. So we're going to look at our domain by thinking about, again, our denominator, just like we would the vertical asymptotes, okay? So we set our denominator, we know that that cannot equal 0. So x minus 1 can't equal 0, x cannot be 1. That means that it could be any real number except for 1. So we're going to start at negative infinity, go to 1, and then union that with 1 to infinity. So everything except that number 1. Okay. So then I look at my vertical asymptote. Again, we can see that x can't be 1. So that's going to be where my vertical asymptote is that x equals 1. For my horizontal asymptote, again, I'm going to compare degrees. Well, the degree of the numerator is 1. The degree of the denominator is 1. So I see that the degree of the numerator is equal to the degree of the denominator. That means I'm going to divide the leading coefficients. So 5 over 1 is 5. My horizontal asymptote would be y equals 5. Wholes appear when there are common factors. There weren't any common factors, so this doesn't have a hole. So this probably looks very similar to something that you did last year. Okay. Let's look at example 2. We have f of x equals 4x over x squared minus 1. Well, first I'm going to factor to kind of help out a little bit. 4x, leave alone. But we know x squared minus 1 can be written as x plus 1, x minus 1. There are no common factors for us to cancel. And so to find our domain, we just want to make sure that our denominator cannot be 0. And so obviously, negative 1 and 1 would make our denominator 0. So x cannot be plus or minus 1. So then in interval notation, what we want to do is we want to set it up. We're going to start at negative infinity until we hit a roadblock. And like anytime we have a roadblock, we're just not going to include that all the way until we get up to positive infinity, okay? So we're going to start at negative infinity, and then we'd hit our first roadblock at negative 1. And then we could start again. We hit our next roadblock at 1. And then we can pick it back up, and there aren't any more roadblocks, so I can go all the way to infinity. Okay, so that's what my domain would look like. Remember, you can have strings of these intervals in that interval notation. Okay. For the vertical asymptote, I look, and I can see again that x cannot be 1 or negative 1. So those are going to be my 2 vertical asymptotes. And you can write them separate if that makes you feel better. X equals 1, x equals negative 1. Okay. And for horizontal asymptotes, I'm going to compare degrees. Here I have degree 1. Here I have degree 2. So I see that the degree of the numerator is less than the degree of the denominator. So my horizontal asymptote is at y equals 0. Okay, using the rules from our chart. A hole is going to occur if we had any common factors that we would cancel. There was nothing that we canceled here, so again, we have no hole that's here. Okay. All right, so let's look at some that may be a little more exciting, in my opinion. All right. Next, we have f of x equals 2x squared minus 3, and then x squared plus x plus 9. So if we look to find our domain, we would want to think about our denominator. We know that x squared, well, and if I try to factor this, I don't really have a lot of luck. Okay, so I want x squared plus x plus 9 to not equal 0. Okay, so what I'm going to do is I need to find the values that I would want to ignore. Okay, so to find that, I would use negative b plus or minus the square root of b squared. So 1 squared is 1, minus 4 times a times c. So 4 times 1 times 9 would be 36, all over 2. Well, do you guys see that this ends up being imaginary? So because only imaginary numbers are going to be an issue, our domain is going to be all real numbers from negative infinity to infinity. Okay. So because there are no domain restrictions, that means that for a vertical asymptote, there isn't going to be one. Sometimes there are special functions that don't have vertical asymptotes. For a horizontal asymptote, we'll compare our degrees. We see both the numerator and denominator have equal degrees of degree 2. So that means that we're going to divide our leading coefficients. 2 divided by 1 is 2. So my horizontal asymptote is y equals 2. We couldn't factor either the numerator or denominator. There aren't any common factors. So for whole, we're going to put none. Okay. Number 4. F of x equals x squared plus 6x plus 9 over x squared plus 4x plus 3. Oh, these can be factored. So let's do that. Now the numerator can factor as x plus 3 quantity squared, but just because I know what's going to happen, I'm going to rewrite it as x plus 3 times x plus 3. And in the denominator, I'm going to factor, and I have x plus 3 times x plus 1. Okay. When I think about the domain, I have to think about this entire denominator, okay? For our domain, we use the whole denominator. And I can see that this right here cannot equal 0, okay? So that means that x cannot be negative 3, and that x cannot be negative 1, okay? So I always look at the entire denominator for our domain. So thinking about going from negative infinity to infinity, I start at negative infinity, I get to negative 3. I can go from negative 3 to negative 1, and then from negative 1 to infinity without an issue. Okay, so there's the domain. But before I look at the idea of the vertical asymptote, we do need to think about our common factors. We didn't have any in the other questions, but do you guys see in this question that x plus 3 is a common factor? That means that this is going to cancel out, and what that's going to do is we're going to have a whole. So there's going to be a whole at that x value instead. The x value that corresponds with that is x equals negative 3. That means there's not going to be a vertical asymptote there. There's going to be a whole. Don't worry, we'll visualize that in just a second. So let's come back to that, do what's familiar to us. Since there's going to be a whole here and not a vertical asymptote, that means the only vertical asymptote will be associated with this factor. So the vertical asymptote will be at x equals negative 1. And our horizontal asymptote, if we look at our degrees, we see that the degree are equal. So we're going to divide our leading coefficients. 1 divided by 1 is 1. Our horizontal asymptote is y equals 1. Okay? So we finally got into this whole. Are you excited? Let's talk about how we would find the whole. To find the whole, what we're going to do is we're going to use x equals negative 3. But the issue is that if we put it in the actual function, we're going to get something divided by 0, right? We'll get 0 over 0, actually. And that's not going to work. So what we're going to do is we're going to substitute this in to what's left after you cancel, okay? So what's left after we cancel is this x plus 3 over x plus 1, okay? And so let's put negative 3 into that, negative 3 plus 3 over negative 3 plus 1. And in this case, we end up getting 0 in the numerator, but we get something in the denominator that's legal, right? We don't get 0 in the denominator. And so this tells me that I'm going to have a whole here, that when x is -3, then the value of our function is 0. So we're going to have a whole at -3, 0. So again, a whole occurs when you have a common factor in the numerator and the denominator. And what we do is we substitute that into what's left after you cancel that out to find where the location of that whole is. Okay. So let's look at graphing a rational function. First, we're going to, again, so we don't get too many vertical asymptotes, we're going to make sure there are no common factors of our numerator and denominator. If so, we'll reduce the common factors and then continue as usual with the simplified rational functions, making sure we use that whole, okay? So we're going to determine the domain. Remember that we have to use the original function, consider the entire denominator, not just the simplified one, okay? The next thing we'll do, just like we did before, is we'll find our vertical asymptotes by finding when our denominator is equal to 0. And I do want you guys to sketch it with dashed dotted lines. Okay? We'll find the horizontal asymptote with those rules, okay, that we had here. We just discussed that. Okay. So now to graph, we're going to include these things. We're going to find and plot the intercepts. Okay. And so what happens here is we're going to set f of x equal to 0 and solve. And that gives us the x-intercepts. Basically, to do that, we can just set our numerator equal to 0. So setting our numerator equal to 0 will give us those x-intercepts. Then we can let x equal 0 and evaluate f of 0. Hopefully, you guys know that that gives us the y-intercepts. We want to make sure to include the whole in our graph if that exists. And again, the whole exists at those common factors. So if there are common factors of the numerator or denominator, that's where our whole will exist. Okay. So for the vertical behavior of the function, the vertical behavior again is going to be on either side of our vertical asymptote. And so if x equals c is, I guess I'll use this color. Sorry, if x equals c is a vertical asymptote, then one way that you can do this is to find the value of the function like just above and just below and see which way it goes. I think what I'd like to do is just look visually. You'll see what I mean when we do an example, okay? So that's going to help us with the vertical behavior. And then when we have the end behavior of the function, that's when we're going to go above and below any horizontal or slant asymptote, which we'll get to in the next lesson. So again, we're just going to do that by extending and comparing to the horizontal asymptote, okay? You can also evaluate a very large number and a very small number and see, again, where that gives you. But again, I think we're just going to look visually. We're just going to extend and again, do this visually. No use in you guys doing extra computations. Okay. So example 5, we're going to graph the function that is from example 4 above. Well, you guys, we have a lot of those things from example 4. In example 4, we've already found the domain, and we've already found the vertical asymptote, the horizontal asymptote, and the whole, okay? So let's refer to that, and let's put that on our graph. So for our vertical asymptote, we said that that was at x equals -1. Okay. Our horizontal asymptote is at y equals 1. Notice my asymptotes are dotted lines. I'm color coding mine. But make sure regardless that your asymptotes must be dotted because they are not part of the graph, they're guides for the graph, okay? So that's step 1, 2, 3. Step 4 is to find and plot the x-intercepts, okay? So again, to find the x-intercepts, essentially what you do is you set your numerator equal to 0. Okay, well, let's put the whole on there, okay? Our whole was at -3, 0. Okay. And a whole, we just legit put like an open circle, like an open hole. So the function isn't going to have a value at that point. So to find our x-intercept, we'll set our numerator equal to 0. We have x squared plus 6 squared plus 9 equals 0. We know that that factors as x plus 3 squared equals 0. So that means that x is -3. So that means that -3, 0 would be our x-intercept. Wait a minute, we said that our whole was at -3, 0, right? So the issue is that this is not going to be that because a whole is here. Again, this doesn't happen very often where your x-intercept is necessarily your whole, but that's what happened here. You know, lots of different things can happen. So that means that there is no real x-intercept. There is no value that will give the function 0. Okay. But we should be able to have a y-intercept as long as we don't have a vertical asymptote at x equals 0. And so again, what you do to find the y-intercept is you just let f, you find f of 0. So all the terms that involve x are going to cancel out. And so I just end up with 9/3, which is 3. So that means that my y-intercept is 0, 3. So 1, 2, 3. So there's my y-intercept. Okay. So that was step 4. We did that step 5, the whole already. And so now what we want to do is determine the vertical and the end behavior. You guys, when it's like this, it's pretty obvious based on your knowledge of the rational functions where this is going to go. We know it's not going to cross our vertical asymptote. So what's going to happen over here, I don't know why I'm starting on the top, usually I start on the left, but what's going to happen over here is that we know that the asymptotes are going to bind that function, right? Like it's not going to cross those pieces. So here I'm going to extend towards the vertical asymptote, and here I'm going to extend towards the horizontal asymptote. I'll do the same thing on the other side. I'm going to extend towards the horizontal asymptote, extend toward the vertical asymptote. Logically, based on what we know about our rational functions, we know that that's what this is going to look like. Okay. The new look of this one this year is probably this whole. But let's also in this, again, discuss the vertical behavior. Okay. So again, for our vertical behavior, you're going to look at your vertical asymptote. Our vertical asymptote is at x equals -1. So we're going to talk about what happens as x approaches -1 from the left and what happens as x approaches -1 from the right, okay? Again, for the vertical behavior, I don't know if you need to write this. You look at your vertical asymptote. Okay? So what's happening on the left? On the left, the function is going down. So as we look to the left, f of x is going towards -infinity. What's happening on the right? On the right of the function of the asymptote, the function's going up. So on the right, f of x is approaching +infinity. Okay. Again, this is what's happening on the left. This is what's happening on the right. Okay. And that's what your vertical behavior statement is going to look like. Okay. Now let's look at your end behavior statement. For your end behavior statement, as always, this is what happens as x approaches positive infinity and as x approaches negative infinity. Again, I don't care the order, okay? But as x approaches positive infinity, let's look to see what happens. Our graph, we see, is approaching our horizontal asymptote. So our function, f of x, is approaching 1. But let's be very specific and talk about what side of 1 it's on. Isn't it on top of that 1? It's above the 1. So because it's above the 1, we're going to put a plus that's there. And if I look at negative infinity, it also approaches 1. But this time it's approaching from the bottom. So I'm going to put a negative that's there. And that's what our end behavior is, okay? And so again, here for the end behavior, this basically is like on top. Oh, I guess I should say from above. And then this is from below. Okay, so it's approaching the asymptote from above, approaching the asymptote from below. Okay. Okay. Continuing on, today we're going to be looking at example 6. We're going to graph f of x equals 3x minus 1 over x squared minus 1. So for this one, the numerator can't be factored. I'll leave that as 3x minus 1. The denominator can be factored as x plus 1, x minus 1. Okay. Notice that there aren't any common factors that I cancel. So that means that there's going to be no whole. Okay. So we don't have to worry about the presence of a whole here. So let's think about our domain. For our domain, I can see from our factor denominator that x can't be negative 1 and x can't be 1. So again, x cannot be plus or minus 1. So in interval notation, I'll go from negative infinity to negative 1, and then I'll go from negative 1 to 1, and then I'll go from 1 to infinity. Okay? Because there was no whole, that means that both of those restrictions indicate vertical asymptotes. So I'm going to have 2 vertical asymptotes, one at x equals 1 and one at x equals negative 1. For my horizontal asymptote, I'll compare degrees. We see the degree of the numerator is less than the degree of the denominator. So that means that y equals 0 will be my horizontal asymptote. Last time we didn't have much luck with an x-intercept. Let's try that here. So for our x-intercept, we'll let our numerator be equal to 0. So 3x minus 1 equals 0. I can see that I'm going to add 1, divide by 3. X is 1/3. So my x-intercept is a point. So I'll write that as 1/3 0. My y-intercept is what happens when I find f of 0. And the written out form, the unfactored form, is actually easier here because, again, we just look at the constants. So that gives me negative 1 over negative 1, which is 1. And so my y-intercept ends up being the point 0, 1. Okay? So let's take this information and put it on our graph. Now, you don't have to do this, but I'm noticing my y-intercept is 1/3 0. And I'm going to have 2 asymptotes, one at positive 1 and one at negative 1. That just looks a little crammed to me. So I'm going to do my graph by halves. I'm going to make this 1 and this negative 1. So 2, 3. So basically I'm going by halves. Okay, you don't have to do that. But then this way, when I make my vertical asymptotes, those aren't like right on top of each other. I just have a little space as far as that goes. Okay. So then I have my horizontal asymptote at y equals 0. Okay, that'll help us with that end behavior. My vertical my x-intercept is at 1/3 0. So here's a half. So maybe a third would be about right here. And my y-intercept is 0, 1. So I see that that's going to be here. Now, a couple things could happen as far as what this vertical behavior is. This one isn't quite as obvious as the other one, right? This time we have 3 different places, like to the left of the asymptotes, in the middle between the 2 vertical asymptotes, and to the right of x equals 1 that we have things. So sometimes what it's nice for us to do to double check on the vertical behavior is to substitute, all right? So around the x equals -1, or around the asymptote. So the first one is x equals -1, right? Here's one of our asymptotes, okay? We want to look what's happening below that and above that. So to get an idea of what's going below that, again, the idea was to, if we can't tell visually, and that oftentimes happens with these rational functions with 2 asymptotes, then what we can do is go just below or just above that x value. And so we're going to go just below -1 by like 0.1. So what is just below -1 would be -1.1. Similarly, we could go just above -1. That would be -0.9. And what we can see is like, okay, where are those points? And then we can have an idea of where that's going to be, okay? So I would just substitute that into my calculator, okay? So I'm going to, sorry, getting rid of the glare here. So I can take 3 times -1.1 minus 1. And then I can divide that answer by -1.1 squared minus 1. Again, you can do that a couple different ways, but you know, stack the fractions in your calculator. Some of you guys like to do that. You know, create a fraction this way. You could type it in -3 times it's just +3. 3 times -1.1, that's probably a nicer, minus 1. And then in the denominator, -1.1 squared minus 1. And then again, we get this idea that it's going to be about -20.5. Okay, I'm not going to plot that, all right? Now I'll do the same thing with -0.09. So I'll have 3 times -0.9 minus 1 over -0.9 squared minus 1. And that gives me 19.5, okay? What this tells me is that when I look at this asymptote, all right, below that, it's going to be going very low, okay? So to the left, it's going to be going down. So that means it's going to be going this way, essentially. That to the left, below -1, it's going to go down. This is telling me that above -1, it's going to be going up. Oops, sorry, okay? So that gives me an idea of where those arrows would be, okay? Let's do the same thing with x equals 1, okay? I need to go below x equals 1, and I want to go above x equals 1. If I go below x equals 1, that would be like f of 0.9. Going above x equals 1, that would be 1.1. I'm not going to take the time to substitute it in the calculator. That's just substitution, right? If I find f of 0.9, I end up getting -8.9. And if I find f of 1.1, I got 11.0. So what that means is that below x equals 1, that I see this negative, it's going to be going down this way. And above x equals 1, it's going to be going up this way. Okay? So the reason that that's helpful with that vertical behavior is because now we have an idea of where we're bound by the asymptotes. I'm going to start in the middle because this is going to make some of you guys uncomfortable. Because of this vertical behavior that we saw, what's going to happen is that we're going to cross through the y-intercept, cross through the x-intercept, and what we see is that we're going to have, it's not a cubic, but a cubic-ish looking equation or a graph that's there, okay? Some people might be very uncomfortable that it crosses this horizontal asymptote, and I understand that because oftentimes we're like, it's not supposed to cross the asymptote. Well, that's a vertical asymptote. With horizontal asymptotes give us guides at the end behavior as x goes to positive and negative infinity. In the middle of these rational graphs, it's okay to cross them. What we are going to use the horizontal asymptotes for, however, is to get the other pieces of the graph. I know that as I go to negative infinity on the left-hand side, that it will not cross the horizontal asymptote as we go towards negative infinity. So that means that this part of the graph is going to be in this part of my coordinate plane. Similarly, because I knew that my end behavior was up over here, as I go to positive infinity, I know it's not going to cross that horizontal asymptote. So it'll be in this portion of the coordinate plane. So what the vertical behavior tests did is it told us like what part of the graph was it going toward. Was it down here? Was it up here? Was it up here? Was it down here? Did this go down from left to right? Did it go up from left to right? Was it more like U-shaped going up or down? That's what the vertical behavior test tells us, okay? So then if I wanted to write my vertical behavior statements based on this, I'm going to talk about what happens as x approaches -1 from the left and what happens as x approaches -1 to the right. And we can see here as x approaches -1 to the left, our function goes down towards negative infinity, as denoted by this negative value, okay? And as as x approaches -1 on the right, we saw that this was going up towards positive infinity. Well, we have a second asymptote, vertical asymptote, so that means that we would need two other vertical behavior statements. What happens on the left of x equals 1 and what happens on the right of x equals 1. So as x approaches 1 from the left, below it, we said that it was approaching negative infinity. And if we look at 1 to the right, we're going up towards positive infinity. And again, that's shown on the graph as well. Okay. In a test situation, I wouldn't have you write 5 million of these, okay? It's good for you to practice. Your end behavior, again, is what happens as x approaches positive infinity and as x approaches negative infinity, okay? And we see that as x approaches positive infinity, we're getting closer to that horizontal asymptote, which is at x equals 0. So f of x is approaching 0. And notice that that's approaching it from the top, from above. So I'll put 0 plus. And as x approaches negative infinity, it's getting closer and closer to that horizontal asymptote, which was at y equals 0, but from the bottom. So I have that negative that's there. So those are the vertical and end behavior statements that we can make. Notice that I'm not substituting like a ton of values. I'm not making a table. I'm just going kind of like above and below each of the asymptotes if I have to. In that last question that we did, I didn't need to do that because it was very obvious where that was going to be. So notice I didn't do any points to the left or right because it was one asymptote. It was pretty cut and dry based on the other points that I found where the branches of the were going to be located. But in this question, because it wasn't obvious, that's when I had to kind of like do a little extra work. Okay. Last question, example 7. It says the Game Commission introduces 100 deer into newly acquired state game lands. The population N of the herd is given by this function, where T is the time in years. Find the populations when T equals 5, T equals 10, and T equals 25, okay? Well, all we have to do is substitute that value in. So I would take, again, I could create my fraction, and I'm going to do 20 times 5 plus 3 times 5. And then 1 plus 0.04 times 5. Again, I'm just substituting 5 in for T. And that gives me about 333 deer. Okay, so I'll just make a little note that N of 5 is going to be about 333. You guys, we would do the same thing for T equals 10. You don't need to see me substitute. If I find when T equals 10, I end up getting about 500. Oh, I should put a unit. Good idea. Okay. And if I substitute 25, I'll get about 800 deer. Okay. We all know how to substitute. Letter B says, what is the limiting size of the herd as time increases? Well, here's the thing. This is looking at what happens as time increases. As time increases, what we're going to do is we're going to look towards positive infinity, right? So that means that this is really asking about the end behavior. And when it's asking about the end behavior, don't we just look at our horizontal asymptote? Okay. So when we look at this equation, if I were to simplify it, if I were to distribute, I would get N equals 100 plus 60t. So I'm going to write 60t plus 100, and then over 0.04t plus 1, just so I can better compare my degrees. Okay. And I can see that this is degree 1. This is degree 1. The degree of my denominators are the same. Or sorry, the degree of my numerator and denominator is the same. So I'm going to take y equals the numerator, the leading coefficient of the numerator divided by the leading coefficient of the denominator. When I take 60 over 0.04, I get 1,500. So if we were to graph this, that means that as we would go towards positive infinity, there'd be that asymptote at 1,500. So what would the answer to my question be? The limiting size would be about 1,500 deer. Okay. It wouldn't really cross that. That would be it. Okay. So I know lots to think about. So hopefully this helped you review what you know about rational functions and get you knowledgeable about wholes and the idea of this specific vertical and end behavior. All right. Have a great day.